Okay, so we're recording. Welcome back, everybody. We're now in the fourth week of class. So as usual, at the beginning of the week, I'm giving you a new homework assignment, which is going to be due next Monday. It's up here on the board, and it's also on Canvas, so you know the drill as far as that's concerned, right? So the next thing we're going to do, in terms of the lecture, is move on to Chapter 6. So we've covered Chapter 5, which is about electric fields for the last 3 weeks. We're now ready to move on to something new, Gauss's law, covered in Chapter 6. So just by a show of hands, if you've taken calculus, particularly Calculus 3, you may have seen Gauss's law before. Has anyone encountered this in any capacity in the past? Okay, only a handful. So it is sometimes taught in calculus, but not necessarily the most common thing to teach. So don't worry, if you haven't seen this before, we're going to go through it, and hopefully by the end of this you'll get an appreciation for Gauss's law. Okay, so we're going to start with somewhat of a definition. Okay, there's a quantity, a new physical quantity that we're going to encounter called electric flux. And let's actually just do another show of hands. The idea of flux, is this something you've encountered maybe in Calculus 3? Okay, so more people are saying they've heard of flux. So that's really what Gauss's law is about. It's this idea of electric flux. So we're going to define the term, we're going to figure out how to calculate this thing, and then see how it relates to Gauss's law. We'll build up to that. Okay, so like I said, we're going to start with the definition of electric flux. And we're going to define this in two different ways. One way is just a simple equation, which you can plug and chug, and it applies in certain simple cases. And we're also going to learn a definition that involves an integral, which you have to use in other cases. Okay, so let's just for the time being consider a uniform electric field. What I mean by uniform is the electric field is the same everywhere. Okay, so it's pointing in the same direction everywhere, and it has the same strength everywhere. That's a uniform E field. We'll also imagine there's a flat surface in the presence of this E field with area A. So this is our flat surface right here. And you can imagine that the electric field lines are piercing through the surface, just like this, right? So what the electric flux tells you, it's basically a way of quantifying how many of these electric field lines, which are shown in blue here, are actually going through the surface. So the more electric field lines you have going through the surface, the more electric flux you have, is what we say. And it's easy to visualize, right? Just more lines going through the surface, more flux. We denote this with this Greek letter. Does anyone know what this is? This guy right here? It's capital Phi. So capital Phi is for electric flux. Okay, so here's how we define it. Here's the equation for phi. Phi is equal to E dot A. Okay, so E, of course, is our electric field. It's a vector. A is our area, okay? And usually we don't think of area as being a vector, of course, but in this case we are. Okay, so of course, if the area is going to be thought of as a vector, the magnitude of that vector is just going to be what the actual area is. So in this case, we just do like length times width, right? But the direction is perpendicular to the surface, okay? So you see in this picture how we're defining the area vector as being perpendicular to the surface? That's A. So if we take the dot product between E and A, we get the electric flux. And if you don't remember how to take the dot product, this is how it works. I take the first vector, which is E, and just take the magnitude of that. Then I take the second vector, which is A, and just take the magnitude of that. And then I multiply by the cosine of the angle between the two vectors. So in other words, my electric field vector and my area vector will make some angle theta with respect to one another. And if I'm trying to find out the dot product of E dot A, I'd have to include the cosine of theta in that. So is this familiar? Hopefully we've all seen dot products before back in Physics 45. I'm just applying the idea of a dot product to this specific equation, okay? Do we have any questions so far? So that's just a formula. We can use it to calculate electric flux. So actually, let's just have you do one of these, okay? We have a uniform E field that has a magnitude of 850 newtons per coulomb. And it's going through this flat surface with dimensions 35 centimeters on this side, 75 centimeters on this side. What I'd like you to do is calculate the flux through the surface. You have the equation that's relevant for this already, right? Remember, it's just E dot A. Okay, and do that when the angle here is 30 degrees to start off, okay? And then repeat the same calculation, but when the angle over here is 90 degrees. Okay, so take a few minutes, try to work this out, talk it through with the people next to you if need be, and then we'll go over it together as a class. So we're just doing the calculation E dot A for this situation here. Someone left a pencil up here. Yeah, for those of you who came in just a minute ago, be sure to get a copy of the worksheet in front of the room. You can do that after class if you want to. It'll be up here. Factor of 10. I think that might be off by a factor of 10. Oh yeah, no, you're right. Okay. All right. Let's take a minute to go through this one. All right. So we're really just at this point applying a definition of electric flux, which is phi equals E electric field dot A, which is the area vector for our chosen surface, okay? And I just want to remind you that when we evaluate this dot product, that's the same as taking the magnitude of E times the magnitude of A times the cosine of the angle between those two vectors, okay? So in this question, we have two cases. One is where the angle is 30 degrees. So in that case, our electric flux is going to be magnitude of E, 850 newtons per coulomb, times our area. So how would I calculate the area in this case? It's a pretty simple one, right?
0.30 times 0.75.
Yeah, just take the length and the height and multiply them because we have a rectangular area, so it's 0.75 meters multiplied by 0.35 meters. We want this in SI units. So we'll take centimeters, convert to meters like this. And then we have cosine of 30 degrees. Someone tell me how that works out. What do we get?
193.
Yeah, we get 193, although technically I should be rounding to 2 sig figs on this. What are the units? Yeah, so I have newtons, I have meters squared divided by coulombs. So basically, it's an electric field unit, which is newtons per coulomb, multiplied by an area unit, which is meters squared, okay? All right, let's do this one. 90 degrees, what do we get? We get 0 right here. I don't even have to plug the rest of the numbers in. Phi is equal to E times A times cosine of 90 degrees. And what do we get? 0. Let's try to actually visualize this, okay? So imagine the angle between my area vector and my E field is 90 degrees. What does that actually look like? Well, if we're imagining this rectangular area, the area vector is perpendicular to it like this, right? And if I have my E field going this way, well, these E field lines are actually not going through the surface at all in this orientation, and that's why we get 0 for the electric flux. Again, it's important to remember what this means. It's just, to what extent is your E field going through the surface? In this orientation, the lines are actually not going through it at all. Okay? All right, so let's keep it moving. So the electric flux, okay, has a more general definition, which we're going to get into right now. And this applies when you don't have a uniform E field or you don't have a perfectly flat surface, which can easily be the case, right? So maybe the E field is not the same exact value everywhere, and it maybe changes as you go from one place to another in space. And maybe instead of like a flat sheet that the E field lines are going through, we have something more complicated like this, okay? So if that's the case, the previous formula is not going to strictly work, okay? So here's what we have to do in a case like this. We're going to have to take this surface, whatever it happens to be, and break it into infinitesimal elements of area. So instead of the overall area A, we just have a tiny little piece of area, which we call dA. Okay, so you see what's going on here? We have a dA vector when I select this piece of the overall area, and then of course we have our E field like this, okay? So what I have is, for that little tiny piece, I have a tiny bit of electric flux through the surface, okay? So for this little bit of the overall surface, there's a little bit of electric flux, and that's going to be given by d phi, so it's an infinitesimal amount, that's where the d comes from, equals E dot dA. But of course, that only includes that little piece. So if I'm interested in the total electric flux for the entire surface, what I have to do is an integral. I have to integrate over all of those little area elements until I've included everything. So in other words, phi for the total is equal to the integral d phi, which is integral E dot dA. Okay? So in general, electric flux is the integral E dot dA. That's the most general formula we have for it. The other one I showed you is just a special case where you have a uniform E field and a perfectly flat surface. Does that make sense? So let's get some practice using this form. Okay? Let's see what happens in this case. So this is an example we're just going to do together. What we have here is a half cylinder. Okay, so you can see it's cut in half right there vertically. The radius is 3.5 centimeters, and the length of it here is 15 centimeters. It's oriented with this flat side right here going vertically, and of course the curved side is going like this. All right, so let's imagine that there's a uniform electric field with with a magnitude of 5,900 newtons per coulomb, going in the horizontal direction like this. The question is, what is the total electric flux through the curved side of the cylinder? So you see what I'm saying here? This curved part has some electric field lines coming out of it. So what we're trying to do is calculate the flux of those electric field lines coming out of that curved part of the surface.
Can we say that there's less flux coming out of the curved side than the one from the other side? If we were to go the other way? Would it be the
Okay,
same thing?
yeah, so it turns out you're seeing ahead a little bit, right? The flux through this flat side, the lines that are coming in through here, is exactly the same as the flux that's going out, because every single line that's going in through here is eventually coming out through there. But we'll get to that in a second. We're actually going to show this two ways. One where we use that idea that you just brought up, and then the other where we just straight up integrate. Okay? So here's how I'm going to propose, before we switch over to the paper and pen stuff, here's how I'm going to propose we break this thing up into little bits of area, okay? Let's take thin strips, okay? A tiny little strip across this way, and then another strip, and then we just add over all of those thin strips to get the total electric flux, okay? So the thin strip will have a little bit of thickness going in this direction, and then it will have a length going in this direction. That's just how we're going to break this thing up into pieces which we can manage. All right? So any questions so far? All right, so let's draw a picture indicating how we're breaking this thing down into segments. So I have my half cylinder. This is what it looks like when we're kind of looking at the face of it. Well, like I said, we are selecting not the entire curved surface, but some little strip, a thin strip along this curved surface. So I'm showing it to you like this. And then, of course, we'd have to include all of those thin strips to get the total flux, but I'm just showing you one of them for now, okay? So what do we know about this thin strip? Well, it has a length L, which I'll show you going this way. It has a thickness going this way, which I'm going to call ds. And then if we wanted to sort of locate where the strip is, we could use an angle. You see what I mean? If I take the angle off of this line to be theta, okay, that would just tell me, like, where is my thin strip? How far do I go to get to this particular strip? But like always, when we're dealing with some kind of infinitesimal piece of a larger object, it has some kind of span to it, right? So we could call the angle that it takes up here d theta. Okay, so hopefully this sort of thing is familiar to you by now, the way we're notating things. Let me zoom in a little bit. Okay. So now, I'm going to draw some things over here. I have my dA vector. This is going perpendicular out from the surface like this. So what I'm showing is it's perpendicular to the actual surface. That's how dA is defined, remember? But my E field is just going horizontally like this. Okay? And then check this out. The angle between my dA vector and my E vector is the same angle theta that I drew earlier. Okay? So I think we've set it up. We've put all the different things we want to indicate on the page. So now what we can do is start writing down some equations. So what did we do? We break the surface into thin strips. That's what we just did. I'm showing you one of those strips. And then the flux through each one is given by, I'm going to call it d phi, because it's an infinitesimal amount of flux. And that's given by E dot dA, okay? So now let's try to see what we can get out of this expression here. Because we have a dot product between E and dA, as always, we can do the following. We can say it's the magnitude of E times the magnitude of dA. That would just simply be the area of the strip, when I say the magnitude of dA, times cosine of the angle between the two vectors E and dA here, which is what I'm calling theta. Okay? So I'm just applying the idea of a dot product to this specific case. Good so far? Okay, so it's going to take us a little work. We'll do it on the side here. But how could I express the area of this strip? So in other words, what would be a formula for dA given the variables that we put on the page over here?
ds times L.
Yeah, so yeah, exactly. It's basically something you can consider to be rectangular, where L is the length and ds is a tiny thickness of it. So I'll write this as ds times L. But then what can I say about ds? This is what we call an arc length, isn't it? Do you guys remember the formula for an arc length? This is going to come in handy. It's going to be r times d theta, because d theta is the span of this little strip, okay? So we're going to write this as r times d theta, because that's an arc length, and then times L. And that's what I'm going to put in over here for dA. That's the area of the strip. So that's E times, I have RL d theta, and then I have cosine theta. So just to rearrange this in a more suggestive way, I have E, RL, all of those are constants, and then I have cosine theta d theta. So just to be clear, this is the electric flux through one of these strips. The idea is now I must integrate over all of the strips to get the total electric flux through this curved surface, okay? So here, integrate over all strips now. And that will give us total flux. So the idea is we take phi, representing the total flux, is the integral over all of these d phi's, and I'm going to plug this expression into the integral now, okay? But I'll notice that I have some constants that I can immediately pull out, which I noted earlier is E times R times L. And then all I'm left with inside the integral is cosine theta d theta. Now, what should my limits of integration be? Okay, so it's important to remember we're measuring theta off of this line right here, okay? So theta equals 0 is right in the middle. That's not going to be one of our limits of integration. Minus pi over 2 to pi over 2, because we go quarter turn this way and then a quarter turn that way. So it's minus pi over 2 to positive pi over 2, and that's not so bad to evaluate. Let's just do it. When I have cosine and I integrate it, what do I get? I just get sine. So this is ELR, and then I have sine theta. When I integrate, evaluate from minus pi over 2 to positive pi over 2. So I have ELR, sine of pi over 2 minus sine of negative pi over 2. And just real quick, what is sine of pi over 2? And what's sine of negative pi over 2? Negative 1. So in the brackets we have 1 minus negative 1, which is 2. So the answer is 2 times E times L times R. All right? So that's just a formula for the electric flux. And again, we're going to learn about why this is a useful quantity later, but for now we're just focusing on how do we calculate this thing, okay? All right, so this was kind of a brute force method, I would say. There is a simpler way to do it, which is what you suggested. So if you look back at the original picture, we had some electric field lines basically coming in this way and then going out this way. So the idea would be, for this half cylinder, for every electric field line that's coming in through this part, it's leaving through the curved part, okay? So therefore, the electric flux through the curved surface, which is what we found, should actually be the same as the electric flux through this flat surface over here, because the same number of electric field lines are piercing through both surfaces, okay? That's the reason why we can do that. And this one is a little easier to deal with, actually. So what I'm saying here is the electric flux through the curved part is the same as the electric flux through the flat part, and that is going to look like this. So now I'm showing you the flat part of the cylinder, and the E field lines coming out like this, and my area vector also pointing this way. That's what it looks like for the flat part. And actually for that one, since the E field looks exactly the same all over the surface, and my surface is perfectly flat, I don't even need to use the integral for this one. I can just say this is E dot A, which is EA cosine of, so when we're considering this flat part, what is the angle between my electric field and my area? It's just 0. They're pointing the same way. Okay? And then what can I say about the area of this guy? Well, this is L, right? That's just the length of the cylinder. And then on this side, I'll have the diameter of the half cylinder, which is 2R. So when I consider the area, that would be 2R times L, correct? So that would be E times the area, which is 2R times L. And cosine of 0 gives me what? Just 1, right? Cosine 0 is 1. So we get the same answer. 2E times R times L, just like before. Okay, so we can do it one of two ways, is what I'm showing you here. All right, go ahead.
I'm confused. Was the flat side of the half cylinder, was that like there was nothing there? We were just evaluating on the curved side?
Yeah, so here, let me just go back. What we did for the integral was we evaluated on the curved side here.
Oh.
And then we said, well, actually, that should be the same result as if we evaluated it on the flat side here. And we did indeed see that we got the same answer. Okay? Any questions?
Actually, 0 again for cosine the 0 degrees on the simpler part.
Cosine of 0 is equal to 1. That's what we did.
Oh, okay.
Cosine 0 is equal to 1. That's just something you need to remember. Anything else? Okay. So again, all we've really done so far is we've defined this thing called electric flux, and we have a little bit of practice calculating it. That is something you'll need to do in general. But now let's think about a closed surface, okay? So a closed surface, what I mean by that is just any surface that completely surrounds some volume of space. So a really good example of a closed surface would be the surface of a sphere, right? If we're just talking about the outer surface of the sphere, it's completely surrounding the inner part of the sphere, so that would be considered a closed surface. A flat sheet is not a closed surface. It's not surrounding anything. So that's the difference between a closed surface and an open surface, okay? And that's an important distinction to make when we get to Gauss's law. So I just want to make sure we understand the difference, okay? So this is just a little bit of notation, but when we're talking about the integral over a closed surface, what we typically do is have the same symbol for an integral that we normally see, but we'll put a little circle in the center. So every time you see this, you know it's an integral over a closed surface, and it's not an integral over an open surface, okay? So that means the electric flux, when we're integrating over a closed surface, is given by this type of integral, E dot dA, okay? So there's one other thing to say about the way this works when we're integrating over a closed surface. And that is, how do we look at the dA vector? When you have a closed surface, it's clear what's on the inside and what's on the outside, right? There's a clear difference between those two. So the convention for the area vector dA is that it points outwards. Okay? And let me just show you, let's say, with the sphere. If we're on the surface of the sphere, okay, the dA vector, as we have been saying, is meant to point perpendicular to the surface, right? So if you think about it, that could go one of two ways. You could be pointing outwards perpendicular to the surface, or you could be pointing inwards perpendicular to the surface. So you have to choose a convention. And what I'm saying is the convention is we choose the outward by convention. Okay, so dA, if we have a closed surface, is pointing out. It's never pointing in. Are we good on that? So dA is pointing out. All right, so I want you to notice something about, the way this works, just looking at the formula. Okay, if we have a closed surface, and overall we have a positive flux, so that means we integrate E dot dA over the closed surface, and we get something positive, that's telling us something. That's telling us that there's a flow of electric field lines coming out overall. In other words, there's more E field lines going out of the surface than coming into the surface. That would be positive flux. And by the same token, negative flux would mean there's a net flow of your E field lines going in. Okay, so in other words, there's more lines coming into your surface than there are coming out of your surface. Yeah?
How is it possible for like more E field lines to come out than like there being the same amount?
We're going to get to that, but it basically means you have some charge inside the surface. Yeah, that's the only way that can happen. Yeah, so good question. We'll get there. So, let me just try to make this convention as clear as possible, okay? Let me just sketch out a few pictures and hopefully you'll see it a little better. Okay, so what I'm trying to convince you of is that lines coming out of your surface is positive flux. Okay, so let's just say that my surface is a sphere like this. Okay? And my dA vector, the area vector, is pointing out, but perpendicular to that surface by convention. Now let's just say I have an electric field, a line that's coming out like this. Okay, so there's my E vector. What can I say about the angle between E and dA?
It's a right angle.
So in other words, what kind of like general statement can I make about the angle between these two vectors? It's a small angle is what I'm getting at, right? If the E field line is coming out, the angle between those two vectors, it can be as small as 0, and then it can be as large as like 90 degrees, where it's just barely grazing the surface, but still coming out, okay? So if I have an E field line coming out, my angle between these two vectors is somewhere in this range. And you tell me, when I take cosine of an angle in this range, what do I get? Cosine of 0, what do I get?
1.
Yeah, so my point is, cosine theta is going to be positive. It's going to be greater than 0 if theta is in this range. And that means my electric flux is going to be greater than 0. So you see what I mean? Because theta has to be in this range, it ensures that we get some kind of positive electric flux if you have an E field line coming out. All right? But if you have lines going into your surface, I'm claiming that's negative flux. And we can convince ourselves that that's the case by drawing a similar kind of picture. You have your surface, and remember, if we have a closed surface, the convention is to say your area vector dA points outwards. Okay? What does it look to have an E field line going in? It just means basically reverse the direction of the E field in the previous picture. That field line is going into the surface, right? Now, what range of angles do I have in this case? I have a pretty big angle, right? Almost 180 as I'm drawing it here. But what range are we talking about generally? So I can be anywhere between like 90 degrees and 180, okay? And if I take cosine of an angle in that range, what do I get?
Negative.
I'm going to get something negative, right? If I have an angle between 90 and 180, and I take the cosine, I am definitely going to get something negative, which means I'm going to have negative flux. So that's just why mathematically this works out, okay? But just, it's an important thing to remember. You have a closed surface, E field is coming out, that's positive flux, E field is going in, that's negative flux, okay? So any questions on this? All right. Oh, wrong thing. There we go. Okay, so now hopefully you're convinced about like when flux is positive, when flux is negative, okay? So now we're going to start to build up to the idea behind Gauss's law, which involves electric flux. Okay? So I want to just remind you of two basic facts. Okay, and one of these facts we established, or actually both of these facts we established in the last chapter. Okay? So fact number one is that electric field lines always start on positive charges and end on negative charges. So the easiest way to see this is to remember, like, if we have a point charge, a positive point charge, we have the E field lines going out away from the point charge in all directions. Okay? And if we have a negative point charge, the E field lines are coming in towards that point charge. So we remember this, right? Number two, the second fact is that how many E field lines we have, either coming off of a charge or going into a charge like this, it depends on the magnitude of that charge. So in other words, if we look at these two pictures side by side, where I have positive Q and negative 2Q, this one, in terms of the magnitude of the charge, is double. So it should have twice as many lines connecting to it. And that's what we see there. Okay? So based on these two facts, we can make a conclusion. Okay? If we have a closed surface, the flux through that closed surface basically just depends on how much charge is inside the surface. So let me say that again. The flux through a closed surface is proportional to the charge that you see inside of that surface. And I think this addresses your question from before. Let's, again, take a look at these two cases. In the first case, we have a positive charge. And this dashed line is meant to denote a surface which is fully enclosing that charge. So the surface is completely surrounding the charge. That's what you should be seeing here. Now, what kind of flux do I have in this case? Positive or negative? It's positive because the E field lines are coming away from the positive charge and they're going out of the surface. So we've already seen that that's positive flux, right? And I have a positive charge on the inside, don't I? What about in this case? I have what kind of flux? It's negative flux because the field lines are coming in, going towards the negative charge. So when I'm basically surrounding a charge that's positive, there's positive flux, and when I'm surrounding a charge which is negative, there's negative flux. But remember, the more charge I have in terms of just magnitude, the more field lines I'm going to have. And the more field lines I have, the more flux I'm going to have. So that's why this works out. That's why the flux through the closed surface just depends on how much charge is inside. Okay? Right, so we just said this a second ago, but let's repeat. So if we have a surface which is surrounding or enclosing a net positive charge, there's positive flux because the E field lines are coming out. And if we have a surface that's enclosing a net negative charge, there will be a net negative flux through that surface. And the reason is the E field lines will be going in that sort of situation. Okay? So are we all seeing this? Hopefully it's clear with just the point charge case. Any questions so far? All right, we'll keep going. So now we're ready to state Gauss's law. Here it is. So as we said, electric flux through a closed surface is directly proportional to whatever charge is being enclosed by that surface. So we can turn this into a more mathematical equation to say E dot dA integral. And remember, when we put this little circle on the integral sign, that means we have a closed surface. So on this side, we just have the total electric flux through a closed surface. That equals Q enclosed. That means how much total charge are we surrounding or enclosing with this surface, divided by epsilon naught. And epsilon naught is a constant that we've seen before. If you recall, we saw this in the previous chapter. Let me just remind you what the value is. Epsilon naught is 8.85, 10 to the minus 12. It has this kind of weird unit of coulombs squared per meter squared per Newton. And it's called the permittivity of free space. That's the name we give to this constant. Okay? So this is a mathematical equation developed by this guy. a German mathematician and physicist who is shown here, Carl Friedrich Gauss. Okay, so that's the statement, and hopefully you see why it's true given what we've been building up to. The last thing to say about the way we apply Gauss's law in practice is that, if we're using Gauss's law to solve a problem, you're going to have some set of charges lying around in space, and you're going to draw some kind of surface that surrounds those charges, just for the purposes of solving the problem. So this surface that we integrate over doesn't necessarily have to be something out there in the real world. It's really just something that we construct for the purposes of analyzing a problem most of the time. So it's not something physically real, it's just something we add to the picture in order to solve a problem. Does that make sense? All right. So with that said, let's see if we understand Gauss's law. So I have a positive charge right here, positive Q. That's the only charge around, okay? And then we'll imagine this surface here. It's spherical in terms of its shape, but that actually doesn't really matter a whole lot. This is our surface. So my question for you is, what is the total flux through this surface? You don't need to put a number to it. Just tell me if it's positive, negative, or zero. What is the total flux going through this surface?
Positive, negative.
Zero.
All right, so we've got all answers. Only one of them is going to be true. Okay, let's put it to a vote. Let's just base this off pure intuition. Who says the answer is A, it's positive? Okay, what about B, negative? Okay, what about C, zero? Okay, if you answered C, you're correct. Now there's a few ways we can actually take a look at this. I mean, the first is just to use Gauss's law straight up, right? If we take a look at this surface, how much charge is it actually surrounding? It's not surrounding any charge. If this were inside of the surface, then it would be surrounding some charge. But as it's shown here, it is not surrounding any charge, is it? So right away, Gauss's law would tell us if we're not enclosing any charge, we have zero total electric flux through the surface. Okay? So it's got to be zero on that basis alone. But another way to see it is this, right? If I just look at this half of the circle over here, right, or of the sphere, I have field lines coming out, correct? So I have lines coming out through this end. So that would be a positive flux just for this part. But for every line that's coming out this way, there's a line going in this way. And a line going in is negative flux. So when we take the net flux, this positive flux and this negative flux cancel out and you get zero.
So if there was no lines that went through, it would be a negative flux?
Yeah, if no lines were going in and just lines were coming out, then we would have positive flux. But the only way for that to happen, actually, if you think about it, is if this charge is inside of here. That's the only way for all of the lines to be coming out. Okay? So that's kind of the idea. So zero flux given. So okay. What about this surface? Okay, we have, and just in case it's not totally clear, we have two charges. One is minus 2q, and the other is positive q, and they're both surrounded by this green surface here. So what is the total flux through that surface? Again, we don't really care to put a number to it, just positive, negative, or zero. So yeah, it's got to be negative because we're enclosing a net negative charge. We're enclosing two different point charges, just add them together for the net charge enclosed. So we have minus q overall, correct? So q, and then add minus 2q, we get minus q overall. And that means we have a negative enclosed charge, we have negative flux. So and let's think about this not just using Gauss's law. So what I just told you is kind of using the idea of Gauss's law to get the answer. But there's another way to see it, right? If I have plus q here and minus 2q here, as we learned last week, that means we'll have twice as many lines coming in towards this negative charge as we have going out away from this positive charge. So overall, we do have more lines coming in than we have going out, don't we? Just because of the difference in the charge. And because we have a net flow of electric field lines going in overall, that is a negative flux, okay? So hopefully you see the idea that we're getting at here. Any questions? Okay, go ahead.
Is it like, cause you see how like it looks like it's trying to exit, but then it goes to it? Is that because it's 2Q and it's not just Q?
Yeah, exactly. So if we had like Q here and then minus Q here, then the flux would be 0 in that case. Yeah, but because of the fact that we're not enclosing a net 0 charge, we do have some flux. Yeah. Okay, so again, this is just another conceptual question. We have only one charge in this problem. Okay, the charge is right here. It's point charge Q. We're assuming it's positive, so you can see the field lines are going away from the charge. It indicates it's a positive charge. So what we're going to do is we're going to surround that charge with two different surfaces. Okay, one of those surfaces is just a nice sphere shown in green, and that area we'll call it A1. And then the other one is kind of irregular, and it's shown in blue, and that area will be A2. So which statement is correct about the flux through the two different surfaces? Is it that the flux through surface number 2 is bigger, the flux through surface number 1 is bigger, or is it that they have completely equal amount of flux for the two that we see here? Think about it. What do we think? Is it A? Is it B? C? Yeah, it's got to be C. There's an equal amount of flux through the two surfaces. Let's make sure we understand. I mean, again, if we just use Gauss's law, which tells us the only thing that flux really depends on is how much charge you're surrounding, we can clearly see these two surfaces are surrounding the exact same amount of charge. So just on that basis alone, they should have the same electric flux, right? But another way to see it is every single field line that goes out through this green surface eventually also goes out through the blue surface. So on that basis too, you should expect the same amount of electric flux, okay? So is this making sense? I'm not sure looking out there if it's making sense. Let me know, okay? All right, we're going to do some more of these. All right, here's an example where we can use Gauss's law. So what we have are electric field lines going out through the two ends of the cylinder, and the radius of that cylinder is 12.5 centimeters. The field lines exiting the cylinder are perpendicular to those endpoints, like this. Okay, we know that the magnitude of the electric field at the left end, which is over here, is 355 newtons per coulomb. And we know that the electric field at this end is different. Let's say it's going to be 785 newtons per coulomb. And then we're also given that the curved part of the cylinder here doesn't have any E field lines coming into it or going out of it. So based on that, what is the net charge enclosed by the cylinder? So here we're going to actually put a number to it. We're not just going to say it's positive, negative, or 0. Eventually we want to actually put a numerical value to it. But I mean, based on what we've said in the past, what do we expect the answer to be? Positive, negative, or 0? It's positive because we have a net flux going outwards of E field lines. We already understand that corresponds to enclosing a positive charge with your surface. Yeah?
Is the reason why it's greater on the right side is because it's closer to that? To the right side?
So, I mean, this is just the way we constructed the problem. There's nothing particularly special about these numbers. And in fact, we can't even really say in any detail how is the charge arranged inside of here. We can just say what the total amount of charge is. That's really all we can take away from this. Okay? But with that said, let's try to do the calculation. All right, so we're all clear on the statement of the problem here? All right, so here's what we're going to use. Gauss's law says integral over some closed surface E dot dA is equal to the total charge enclosed by that surface divided by epsilon naught. So another way to say this, just I want you to be able to kind of be a little flexible in the way you write things. E dot dA is just electric flux. So I could also just write this as phi. The electric flux through the cylinder is equal to Q enclosed divided by epsilon naught. And so that's what I'll do for now. Now in this case, what we want to know is Q enclosed. We want to know how much electric charge is being surrounded by this cylinder. And so we'll just rearrange to say that is equal to epsilon naught times the total flux phi. Okay? But here's what we're going to do with that. Let's see. Do I have something? Okay, here's a cylinder, right? We're going to break the flux into three parts. We're going to say, what is the electric flux through this end cap, the circular end over here, and then also the circular end over here, and then we'll just take the curved part to just be one big area that we take the flux through. Okay, so we're going to break it into these three parts. Make sense? Okay, so I have epsilon naught. I have the flux going through the left end cap of the cylinder, so I'll just write that as phi left. I have the flux through the curved part, okay, and then I have the flux through the right end cap. And since I'm talking about a closed surface, I need to really include all of that to have a fully closed surface at the end of the day, okay? Now, one of these three in this problem is going to equal 0. Will you tell me which one of these three is going to equal 0? Yeah, because we're just told in the problem that there is no electric field lines going through the curved part, so therefore there's no electric flux through the curved part. It's only through the end caps. So this is going to equal 0 because there's no E field lines going in or out. Through that part at least, okay? So that really just means we need to take a look at the left end cap and the right end cap, okay? And so for the left end, I'll just draw it real quick. We have a circular area, and remember, the area vector points out away from the inside of the surface. So like, this would be my area vector for the left end cap, pointing outwards. And if you recall from the picture, I also have an E field, which is pointing to the left as well. And since I have a different amount of electric field on each side, I'll just call this like E left. Does that make sense? Now this E field is actually uniform over the surface. It takes on the same value at all points along the surface, and it's pointing in the same direction. So I don't actually even need to do an integral here. I can just do E dot A because it's uniform. But for the right end, I actually have something looking quite similar. It's going to be my area vector pointing to the right, because that's the direction going outwards away from the inside. And then I have some kind of electric field here, which we'll call E right. So that's the basic picture as to what's going on and what we need to know in order to calculate flux. Does that make sense? So for each one of these, we're going to do this calculation. We're going to say flux is E dot A, which means we can take this to be E times A times cosine of, okay, tell me, for both of these cases, what is my angle between the E field and the A vector? It's 0. It doesn't matter if we're on this side or if we're on this side, because E and A just point in the same exact direction, we have 0 for the angle Okay, so when we take this dot product and express it in terms of an angle, we can plug in 0. Okay? Okay. Cosine of 0, what does that work out to again? 1. So that's just 1. And then we have E times an area. What should I be using for the area? What formula? Yeah, it's a circular area that these E field lines are going through. So we would use pi r squared in each case. So if I want the flux through the left end, I'll take the E field there times pi r squared. If I want the flux through the right end, I'll take the E field over there times pi r squared. Does that make sense? That's what we're going to use. And then again, for the curved parts, there is no electric flux. So therefore, Q enclosed equals epsilon naught. Flux through the left end is going to be E field at the left end, pi r squared. Flux for the curved part is going to be 0. That's what I'm putting in here. And then flux through the right end is going to be E field at the right end times pi r squared. So now we can just plug numbers into this and get the answer. Okay. So epsilon naught is 8.85 times 10 to the minus 12, and the units are coulombs squared divided by newtons times meters squared. That's just the units that are attached to this constant. I also have pi r squared as a common factor, which I'm just going to pull out here to the front. So the pi is now in the front. The radius was 12.5 centimeters. So in meters, that's going to be 0.125 meters, and I'm going to square it. So that's pi r squared pulled out to the front. And then, what am I left with? The two E fields on each side added together. Okay? So on the left side, what I had was 355 newtons per coulomb. And on the right side, what I have was 785 newtons per coulomb. Okay, so these are the numbers we're going to multiply together. So someone out there, real quick, just punch this into your calculator. And while you're doing that, we'll take a look at the units. Okay? So I have meters squared from the area, canceling out with meters squared from the epsilon naught constant here. So meters goes away. Newtons also goes away because I have that one time on the top and bottom here and here. And then one factor of coulomb squared here gets canceled with this. So we just end up with coulombs, which is what we should expect. It's some kind of charge after all, right? All right, so someone tell me, how much charge does that work out to? 4.95 times 10 to the minus 10 coulombs. We were able to determine that purely based on how much electric flux the charge is actually producing for us. Okay? So do we have any questions on this example and how it works? Okay. I'm going to give you a slight variation on this one for you to work out. Okay, so everything is the same except one thing. The E field at the right end is now going in towards the cylinder as opposed to coming out. Okay? But all the other values are the same as before. So in this situation, same question, what is the total charge enclosed by this cylinder? So before, we were able to just look at the situation and before we had a number, at least determine that it should come out positive, right? In this case, what do you expect for the total amount of charge in here to come out to? Something positive, negative, or 0?
Negative.
Okay, and can someone explain why we'd expect it to be a total negative charge inside of here? Yeah, we have a bigger electric flux going in than we have coming out. And if we have a net flux going in, we know there's a negative charge inside of there somewhere, right? That's the idea. So try to work out what the value is. You can use a lot of the same, stuff we just established, and then change it slightly to get this answer. So take a few minutes, see what you get, and then we'll go through it together. Yeah, so you just see you flip the sign on
Yeah,
that one term. Okay, looks like the number of you already have the answer. Can someone throw it out?
Negative 1.87 times 10 to the negative 10.
Yeah, so if you do this, you should get minus 1.87 times 10 to the minus 10. Let's go through it real quick. And like I said, the only thing that's changing here is what's going on at the right end. So let's just take this picture and see how it's changed. So at the right end, we have this circular area, and A still points outwards like this. That's the area vector always points outwards in Gauss's law. So that's already been established. But what's changed is now the E field is going the opposite direction as before. So the E field on the right side is now going this way. Now what is the angle theta between these two vectors in this situation?
60.
It's not 0, it's 180. They're pointing in the opposite direction, okay? We have to consider this angle to be 180. Does that make sense? And because of that, we pick up a negative sign in the flux formula. So here, the electric flux on the right side, remember, would be E dot A. And we would just write this as the electric field on the right side magnitude times the magnitude of A times cosine of 180, which as we said is minus 1, right? So this brings out an overall negative sign. So if we take the negative of the electric field times A, that's the flux, okay? So really, if we just kind of start right up here, where we had this line of work in the previous question, all that's happening is this sign becomes negative now, okay? So if you'll allow me, I'll just skip right to this line of work, because everything up until this point is the same, except this sign now becomes negative. So we have Q enclosed equals epsilon naught times, okay, so the flux at the left end is still positive, because the lines are coming out from that end. E left pi r squared. The flux through the curved part is still 0. And this flux is now negative, because we have the lines going into the surface. Electric field at the right side times the area, which is still pi r squared. So basically, take this calculation, and I'll leave out the units because we already saw how those worked out.
You move the picture up a little bit.
Yeah, 8.85, 10 to the minus 12 as epsilon naught. Pi times the radius, which is 0.125 meters, and square it. And then we'll take 355 as the E field over here, and then minus 785 as the E field over here. Okay, and like you said, you'll get minus 1.87, 10 to the power minus 10 coulombs. So the negative sign comes out naturally in this calculation. Okay? Any questions? All right. So let's keep it moving. So I've shown you so far what electric flux is. Hopefully you understand how to calculate it in some examples. And then we also introduced Gauss's law, which is completely based around this idea of electric flux. So Gauss's law is useful in a whole lot of different ways, but one of the major applications that we're going to see is you can use Gauss's law to actually calculate an electric field. Okay, so the rest of the lecture today and most of the lecture on Wednesday is going to be about how we can use Gauss's law to calculate an electric field. Okay? So let's just take a really big picture look at what methods we currently have in order to calculate an electric field. Now, some of these methods we learned about in the previous lecture back in chapter 5. So remember, in the previous lecture, we learned how to use Coulomb's law in order to calculate an electric field. And remember how this goes? We take some kind of continuous distribution of charge, whether that be over some kind of line or some kind of sheet or whatever the case may be, and we break it into infinitesimal elements, which we call dq. And then once we've expressed the electric field due to each one of those elements, dE, we can integrate over all of them to get the total electric field. Now, I'm calling this kind of like a brute force approach because the math can get pretty messy, as you've seen, and it's really just not the most sophisticated thing in the world. We're just breaking the problem into little pieces and then adding up all the pieces, right? We can also use Gauss's law to do the same exact thing. So if we have some kind of distribution of charge sitting in space, we can ask the question, what is the electric field that it produces? And we can use Gauss's law to actually solve the problem, okay? Now, Gauss's law is usually a little bit more mathematically clean. There aren't as many crazy integrals floating around where you have to make U substitutions and trig substitutions. That's going to be mostly gone when it comes to Gauss's law. The math will be simpler and cleaner. However, you got to be careful because you can't always use this to solve that kind of problem. You can only use this to solve for E if your problem has a certain kind of symmetry associated with it. And we'll get into, what are the different symmetries where we can use Gauss's law. I'll explain that, but just keep in mind it's really only useful in certain special cases, okay? And the basic idea is this. If you take a look at the equation for Gauss's law, and you were to ask the question, what is E? How can I solve for E? The only way it would ever work is if you were able to pull E out of the integral, right? I would have to be able to pull E out of this integral in order to actually solve for it, right? And if I can't do that, then it's pretty much hopeless to use Gauss's law to solve for the E field, okay? So that's why it's only certain special cases where we can do that, okay? Good so far? So now let's get into those special cases. Or in other words, what are the different types of symmetry that we can have where Gauss's law will apply? So when we talk about a distribution of electric charge being symmetric, what we mean is if you do something to it, whether you rotate it or you flip it around or you shift it in some way, it still looks the same even after you do that. That's what we mean by symmetry, okay? So let's get into the three types of symmetry, and we'll start with this one, spherical symmetry. So when we have a spherically symmetric distribution of charge, it means if we rotate it around some kind of central point by any amount, it still looks exactly the same. So let me take this as our example. We have a ball with a bunch of positive charge distributed over the outside of it, right? So if you were to imagine taking this ball and rotating it around the center, you can rotate it this way, that way, any way you like, it would still look exactly the same. It would still just look like you have a ball with positive charge all on the outside. So by rotating it in this way, we don't really change the way the distribution of charge looks, and therefore we have what's called spherical symmetry, okay? So let me be a little bit more explicit about what has to be happening here to have spherical symmetry. It basically means charge density. Remember what that means? It's like charge per unit volume. Only depends on your distance from a central point, okay? If charge density depends on anything else, like an angle, let's say, then it doesn't have this type of symmetry. So if it only depends on your radius, in other words, it has spherical symmetry, okay? Another type that we're going to see is cylindrical symmetry. So when we have a cylindrically symmetric charge distribution, that means the charge distribution looks exactly the same even if we rotate it, not around a point like with a sphere, but around a central line. Okay, so actually with this, let's get out our classic cylinder. If it has cylindrical symmetry, it means if I rotate it around a central line this way, it remains unchanged. That's the idea. So the example I'm showing you here is just a cylinder where we have positive charge evenly spread out over the exterior of it, right? And you can imagine if I were to rotate that in any direction this way around that central line, it would still look exactly the same. And that's why it has that type of symmetry. Okay, that's what it means. So what has to happen for this symmetry to be, applicable? It means the charge density only depends on distance from the center of the cylinder. So it's not radius as in distance from the center of a sphere, it's radius as in distance from the center of a cylinder, but if that's the case, you have cylindrical symmetry, okay? And then the last one is called planar symmetry. So what kind of symmetry are we dealing with here? In other words, what way can we sort of shift or rotate things and it still looks the same? When you have planar symmetry, that just means if you shift along the plane in any direction, just move up, down, left or right along the plane, it still looks exactly the same. So in this case, imagine you had a really big sheet of charge where, in this case, let's say there's negative charge evenly spread out throughout the sheet, right? So if I'm located here, I look around and I see a certain distribution of charge. If I move over, still looks exactly the same, right? If I move down, still looks exactly the same. That's what I mean by being able to shift along the plane and nothing really changes, okay? So when we're dealing with planar symmetry, that just means you have a uniform charge density over some plane or over some sheet, okay? These are the three cases where we can actually use Gauss's law to solve for the electric field. If it's not one of these three cases, it's not going to work, okay? So we'll go into some detail and go through a lot of examples about how to use each one of these cases, okay? So any questions so far as to where this is going? Okay. Yeah?
What is square root? Cube.
No, a cube? Yeah, so that wouldn't have this type of symmetry, as it turns out. It would have to just be a sheet. Yeah. Okay. Okay, now let's, before we go into the first example, talk a little bit more about this symmetry stuff, because it's a little subtle, and it's important to be able to understand what we're doing here. So the reason we can exploit symmetry is because, when you have a certain distribution of charge, and it has a certain type of symmetry, the electric field it creates has the same exact kind of symmetry. So in other words, if I have spherical symmetry in the way my charge is spread out, that means I have spherical symmetry in my electric field. If I have cylindrical symmetry in the way my charge is spread out, I have cylindrical symmetry in my electric field. So they share the same type of symmetry, the way your charge is spread out and the type of E field it's producing. They're symmetric in the same exact way. And that's what it is actually useful here, okay? So let's take a look at, let's say, the spherically symmetric case. We can say with certainty what the E field should look like, okay? We don't even need to know the details of how the charge is spread out. We just need to know that it has spherical symmetry. And once we know that, we know the E field looks like this. It's basically just radiating outwards in all directions, assuming it's positive charge. Of course, if it was negative, the lines would be going in. But the point is it has that spherical symmetry to it, okay? In the same way, let's say we had cylindrical symmetry on our charges. That would create a cylindrically symmetric E field. That would look like E field lines pointing out in all directions away from that central line, whatever that happens to be. Or again, if it were negative, they'd be pointing in, but it would still have this general shape to it, okay? If we look at the planar case, here's what that looks like. The E field lines are basically just coming up off the plane in a direction that's perpendicular to the plane, okay? So right now I'm just claiming that these things are true. I'm going to go through in some detail how this case works. And hopefully you'll be convinced that, yeah, this is really the way the E field has to look. There's no other way it could work, okay? So let's get into that. All right, so again, this is kind of a subtle argument, so stop me if you need any clarification on this. But what I'm going to do here is suppose that we have a spherically symmetric charge distribution. Okay? So we have some kind of spherically symmetric charge distribution, but just we're imagining an E field that is not spherically symmetric. And what I'm going to try to convince you of is this doesn't make any sense. We can't have a charge distribution that's spherically symmetric creating an E field that is not spherically symmetric. They have to both be spherically symmetric. So the classic example of a charge distribution which is spherically symmetric would be literally imagine a sphere containing positive charge evenly spread out along its outer surface. Okay? Now I can come up with a lot of examples of an E field that's not spherically symmetric, but here's one of them. So maybe we imagine the E field is doing this. It's radiating out in all directions at the bottom, but then somehow it's just zero up here. Okay? So this is wrong, of course, but just imagine that this is the case. Okay? So one thing we could do with this picture is we can imagine flipping this entire thing like this. Okay? In other words, we're going to flip the entire picture about this line, which I'm showing you here. Okay? And when we make that sort of flip, what do we see? Well, the charge distribution looks exactly the same as before, right? Because it still just looks like positive charge evenly spread out over the outer surface, right? But now what is my E field going to look like? Which direction is it pointing if I just flip the whole thing over? So now I would have E field lines kind of pointing up for the top half and then nothing down here when I make that flip. See, that doesn't make any sense, does it? Because how can it be that I've made no change whatsoever to the way the charges are distributed, but I've changed the E field? See, that doesn't make any sense. Because it's these charges, after all, that are creating the E field. And if I haven't changed the charges, I shouldn't be able to change the E field, right? So that's telling us that since my charges have this type of symmetry, my E field also has to have that same type of symmetry. It doesn't make sense that they would not share the same symmetry. It just doesn't track with what we know. Okay? And I'm not going to get into the other two cases with the line of charge and the plane of charge, but you can do something very similar to show that your E field should have the same type of symmetry as the charge distribution in those cases also. Okay? So what we'll take away going forward is that if you have a spherically symmetric distribution of charge, this is what the E field will look like. It's radiating evenly outwards in all directions. This is what it will look like if you have cylindrical symmetry, and this is what it will look like if you have planar symmetry. Okay? Okay, so moving on. I want to make sure we understand this point. We have diagrams, example 1, example 2, and example 3. Okay? For each example, what I want you to see is what kind of symmetry do we have? Okay? Just basically answer yes or no whether we have spherical symmetry or not. Okay? And then once you've established whether or not we have spherical symmetry, try sketching what the E field lines look like, at least when we're outside of the sphere. Okay? So try that for example 1. Again, try to see if we have symmetry. Then draw the E field lines. Do it for example 2, and then do it for example 3. So on your paper, try sketching out these E field lines. See what you get. Yeah?
And if the number of pluses and negatives, minuses, are those going to be like accurate to what you want the charge
Yep.
of each one to be? Like?
Yeah, exactly. So this should be representative. Okay. So here, let's start with the first question. Example 1, is this a spherically symmetric distribution of charge?
Yes.
It is, because how do we know? If we were to take this and rotate it around the central point, the distribution looks exactly the same, okay? Because what I'm trying to get at here is we have positive charge evenly spread out around the outside of it, okay? Okay, what about example 2? Is this spherically symmetric?
No.
No, because it's clear that if I were to rotate around the central point, I would actually change the way the charge is distributed on the outside, right? For example, I could like take the negatives and put them up here by just rotating. So it's not sharing this type of symmetry. Okay, what about example number 3?
Yeah.
Yes, okay? So even though it's a bit more complicated than this case, it has this property where if we were to rotate this thing around a central point, it would look the same. Or in other words, the type of charge density we have really only depends on your distance from the center. Okay, so we have like negative charge density in the middle, and then going to positive, but it only depends on your distance from the center. It doesn't depend on anything else. Okay? Yeah?
Example 3 to 0.
Let's see. Let's count them up. How many positives do we have here? 1, 2, 3, 4, 5, 6, 7, 8, right? How many negatives? Yeah, so it's slightly more negative charge. So we have, if we're out here, E field going inwards. Yeah. So let's actually draw these pictures now, so we understand. So example 1, that was a spherically symmetric distribution of charge. And you can see that. We already explained why. That means when we draw the E field, it also should be spherically symmetric. So if we're looking at the E field outside of the sphere, because it's a positively charged sphere, the E field lines will be going out in all directions. Okay? So that's very useful that we know the E field has this general shape to it. Okay? Good so far? All right, what about example 2? That's not symmetric, right? So it's not spherically symmetric. And that's because when we draw the charges, we have like positives on top of the sphere and negatives on the bottom. What does the E field look like generally speaking here? What direction should E field lines be going in this picture?
To the top.
They should be starting at the top where we have positive charge and then actually ending at the bottom. So something like this. And clearly this is not the type of E field that is spherically symmetric, right? Okay, so we would not be able to use Gauss's law to solve this kind of problem. But we would be able to use Gauss's law to solve this kind of problem. Okay? And then let's do example 3. That one is spherically symmetric. And in this case, we counted up the charges. We have slightly more negative charges on the inside of this sphere. So we'll show E field lines going in a way that looks spherically symmetric. Okay? So we all clear on this, how this works? All right then. So I think we've laid the groundwork enough that we can go to our first actual example where we calculate an E field using Gauss's law. And we're going to start with the simplest possible case, which is a point charge. Okay? All we have is a point charge, positive Q, sitting here, and we want to know what the E field is. Now, we already have the answer to this. We know it's given by Coulomb's law. KQ over R squared would be the E field. But we're going to derive that actually using Gauss's law. Okay? We're going to verify that we get the same answer that we've already seen before. Okay? So let me show you the steps we're going to take to do this. We're going to start here. Just sketch what the E field looks like. Because we have just a single point charge, the E field should be spherically symmetric. So it should be radiating out in all directions. And that's already something we know. So let's just indicate that on our diagram. Okay? Now that we've established what the E field looks like, here's what we do next. We're going to draw a surface. This is the thing that I mentioned earlier called our Gaussian surface. It's going to surround the charge. And what shape should we choose for our Gaussian surface here? Yeah, spherical symmetry. It's natural that we would choose a sphere for our Gaussian surface. Okay, so this is, again, it's not a real sphere that exists in the real world. It's just something we construct for the purpose of solving the problem. And so for that reason, we typically are going to show that with a dashed line. It's kind of like an imaginary surface. So we indicate that with a dashed line. So what is the Gaussian surface? It's a spherical shell, radius lowercase r, and it's centered on the point charge. Okay? So there it is. So now it's all set up, and we can apply Gauss's law, which says the integral of E dot dA over the entire closed surface here is equal to the enclosed charge, which is just Q, that's the charge we're surrounding, divided by epsilon naught. Okay? So what I'm going to do here is take the left-hand side of this equation, which says E dot dA, and break this down a little bit. Remember, any dot product can be written as the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between the two vectors. So I'm really just taking the dot product and re-expressing it in this way. Okay? But can anyone tell me what would the angle between my E vector and my area vector for this surface, what would the angle be?
90.
It would be 0. Let's see if we can convince ourselves of this. What direction does the area vector point when you have a closed surface?
Outward, right?
It points outwards, perpendicular to the surface. Okay? So, I mean, the dA vector kind of depends exactly where you are, of course, right? But let's say we're here. My dA vector would be pointing outwards like this. But the point is, it's going in the exact same direction as my E field. My E field is pointing radially outwards, and so is my dA vector. It's pointing radially outwards. So the angle between those two vectors, regardless of which point on the sphere we're talking about, is 0. Does that make sense? We're pointing the same way. So because the E and dA vectors are parallel to each other at each point on this surface, meaning theta is equal to 0, we can plug in 0 for cosine, or cosine of 0 right here, and that gives us 1, right? Cosine of 0 is 1, if you remember. Okay, we also know, because the E field is spherically symmetric, right? It's going to be the same at every point along this surface. In other words, the magnitude of the E field is going to be the same at every point along this surface. Because the magnitude of the E field only depends on your distance when we have spherical symmetry, right? The magnitude of E only depends on how far away from the charge we are, right? And if I'm considering what E looks like over this surface here, well, it's going to have the same magnitude because we're at the same distance away from the charge at every point along that surface. Okay? So what that allows me to do is pull magnitude of E out of this integral because it's constant over the surface. And that's exactly what I want to do, right? If I'm trying to solve for E, I better be able to make this move at some point where I pull it out of the integral, okay? And then the only thing I'm left with is the integral over dA. So that would just be my total area for the spherical surface. What would the surface area of a sphere be? Remember the formula? It's 4 pi r squared. Okay? The total surface area of a sphere is 4 pi r squared. So when we integrate over all the little bits of area, we get the total surface area, which is 4 pi r squared. Okay? So we have magnitude E times 4 pi r squared, that's the total area, equals Q divided by epsilon naught. What does that mean for magnitude of E? Just divide out this part right here. So we have magnitude E equals Q divided by 4 pi epsilon naught r squared. And remember, 1 divided by 4 pi epsilon naught is the same as K. So you could also write this as KQ over r squared. So that's just Coulomb's law. Okay, so it's important to see what we just did. We already know this should be the answer, right? We've seen this already. But we were able to get here by using Gauss's law. Okay, and this is probably the simplest case of Gauss's law, where you just have a single point charge. The other cases we'll see are going to build up in complexity. Okay? Any questions? Okay, so that's how it works. Let's look at another example. Yeah, we have time for one more. So here's what's going on here. We have a conducting sphere. We have a spherical conductor, and its radius is capital R. It has a net charge of Q, which is uniformly distributed on the surface. So just really important to note, we have a sphere, and all the charge is on the outer surface. None of it is on the interior. It's all just on the outer surface, okay? That's what's going on. So what we're going to do is find an expression for the electric field as a function of lowercase r, which is the distance from the center of the sphere. So we want to have some general formula for what the E field looks like as a function of distance from the center, okay? Now, in this case, as I'll show you, we're going to have to break the problem up into 2 different parts, okay? So here's what we're going to start with. Imagine this is our Gaussian surface. It's a sphere, it's got radius lowercase r, but that radius is less than uppercase r. So in other words, we're inside of the conductor. Okay, we're not outside of it, we're inside. Can anyone tell me, if this is our surface, how much charge are we enclosing? How much charge are we surrounding?
Should be none, right?
It's 0, because we're told all the charge is on the outside here. So if our Gaussian surface is on the inside, there's no charge, there's no net charge on the inside. So we're enclosing 0 charge with this surface, okay? That makes sense? If we're enclosing 0 charge, what does that tell us about the E field?
0.
It's also going to end up being 0. That's right. So the first part of this is pretty straightforward. Because we're not enclosing any charge right here, if you apply Gauss's law, you'll easily be able to see that the electric field is equal to 0. Okay? Okay, so as long as we're inside, there's no electric field. Okay?
Would you say inside being all the purple shaded?
Yeah, as long as we're on the inside of the conductor, there's 0 electric field. That's what we've just found. And the reason for that is because all of the charge is on the outer surface. So as long as we're inside of it, we're never enclosing any charge. Okay? Now let's do surface number 2, which is outside of the conductor. So here we can't just say the E field is 0, because now we clearly are enclosing some amount of charge, right? How much? Q, right? Just whatever charge is on the outer surface here. With Gaussian surface number 2, we're enclosing the whole thing, okay? Make sense? We're closing the whole thing this time. So now we actually have to do some work, so let's go through that work. All right? Okay, so going through this now. So what we found, just to summarize, is that when we applied surface number 1, which was inside the conductor, the charge that we were enclosing was 0, and therefore when we apply Gauss's law, that means E is equal to 0. Okay, so now what we've moved on to is surface number 2, where the radius of our Gaussian surface is bigger than the radius of the conductor. So that's the difference between small r and big R, just remember. And now we're outside of the conductor. All right, so here's what we're going to do. We're going to draw the conductor with a solid line like this. It's a spherically symmetric distribution of charge because we have charge evenly spread out over the outside of it. So what does my E field generally look like? So the lines are going out in all directions. They're going radially out in all directions. So I'll show that like this. So that's my E field, correct? But our Gaussian surface, which I'll show with the dashed line once again, looks like this. Okay? And my area vector always points out away from that surface. That's the convention. So actually, let's just work out on the side what the integral E dot dA over this surface looks like. Okay? So, we'll start as usual by evaluating the dot product. So we have, let's say, magnitude E times magnitude dA times cosine of the angle between the two vectors E and dA. And what is that angle here again? It's 0. They both point radially outwards, so there's no angle between them. Okay? Okay, so we have that. Cosine 0 goes to 1, so we can basically just drop it. Okay? Also, E is something we can now pull out of this integral. Why is that? Because the strength of the electric field is the same at every point along this surface. The only thing the strength of the E field depends on is your distance from the center, because it's spherically symmetric. And that means at every point along this sphere, we're the same distance away from the center, so we have the same E field strength. Okay? That's why we're able to pull it out. Because E is uniform over the surface. That's why we were able to make this move. Okay? And then we just have integral over the surface dA. What was that again? Yeah. Because let me just write this explicitly. When we integrate all the little dA areas, we just get the total area, right? And that, for the surface of a sphere, is 4 pi r squared. That's where this is coming from. Okay? So actually, you see how this worked out exactly the same as before? Whenever we have spherical symmetry, this is E dot dA. Okay? It's always going to work out this way if we have spherical symmetry. Every single time. Make sense? Okay, so therefore, we're going to apply Gauss's law, which says integral E dot dA equals Q enclosed over epsilon naught. So here, Q enclosed is equal to Q, the total charge. So as long as we're outside of the conductor, when we draw a spherical surface like this, we enclose the entire charge on that conductor. That's what I'm trying to say here, okay? So here we have E times 4 pi r squared That's our E dot dA integral. And then on the other side, we have Q over epsilon naught. So guess what? Looks just kind of like a point charge once again. As long as we're outside of the distribution, okay? So on the inside, we actually had 0 E field. But if you have a spherically symmetric distribution of charge, and you're outside of it, you will always get Coulomb's law back. That's something that's generally going to happen, okay? So are we good on this?
The electric field on the outside of the conductor is the same as the electric field inside the conductor.
No, inside the conductor, we found it was 0.
So would it, like, why wouldn't it be like, because doesn't lowercase r mean like the distance from the inside of the conductor to the outside surface of Gaussian?
It's because when we're inside this term, Q enclosed is equal to 0. If this is 0, that's going to ensure, like imagine I plugged in 0 right here. I would just, for Q, right? I would get 0 for E. That's what's happening when we're on the inside. Yeah. Okay, so we're going to summarize this one, and then we'll wrap it up. So what we found is the magnitude of E is Q over 4 pi epsilon naught r squared, which actually just looks like Coulomb's law once again. And in general, what we can say is if you have a spherically symmetric charge distribution, as long as you're outside of it, which is what's happening here, you'll recover Coulomb's law for the E field. Okay? So here's the summary of what this looks like, okay? So we said if we're inside the conductor, in other words, little r is less than big R, we're going to have 0 electric field, okay? But then when we're outside of the conductor, where little r is bigger than capital R, we get this expression. So what does that look like if we were to, let's say, graph the electric field? This is something you're going to be asked to do on the homework. So on this axis, I have the electric field itself. And on this axis, I have radius, distance from the center. So it's just 0 all the way until we reach the outer surface. So that's what's showing here. We're just E equals 0 on the inside. And then on the outside, what's the general form? It's a 1 over r squared type thing. If you plot a 1 over r squared dependence, it looks like this. It's a line which is actually curved and approaching 0 as r gets bigger. And that's our inverse square law. So there's kind of a disconnect, actually, in the E field. We're at 0, and then we suddenly jump up to here, and then follow an inverse square law going down. Okay, so that's going to be it for today. We'll do more examples like this with other types of symmetry on Wednesday.